I'm Austin Schuh from Blue River Technology, and I'd like to talk about testing on embedded systems with remote execution. So, I like to work on things that move. For fun, I spend time with high school students and we program robots. For my job, I program large agricultural equipment. We've seen in previous Bazel conferences that folks use Bazel for autonomous vehicles. BMW gave a presentation a couple years ago. SpaceX has been using Bazel. I find software a lot more interesting when the thing that I'm programming moves. So at my previous gig, we were working on Class A trucks and doing driver assistance systems. Imagine I came to you with a change I wanted to make on the vehicle and said, hey, can you go take this out on the road and test it? What would constitute enough testing for that? If I told you I ran the unit tests on my laptop, is that good enough? Would you feel comfortable? If told you I ran all the nightly tests on a big server, ran a bunch of hours of testing, would that make you comfortable? What is enough testing? Running tests on your laptop is not quite the same as running them on a target. For the vehicle I showed you before, that's a 32-bit ARM machine, which is a bit different than your 64-bit laptop. Pointer sizes will change, size of ints, size of longs can change. Those will have different libcs, lib standard C++ with different bugs and different issues, different operating systems, different kernels. For us, a big one we run into is your laptop's going to have a different GPU than the target. These just aren't quite good enough when you're trying to trust that your test results are applicable so you can roll out your software. So these embedded systems are different than servers. They're going to be part of a mechanical system generally, something that moves. There's a lot of custom hardware. You'll have custom boards, custom peripherals, they'll interact with physical things. This is all quite different than your server. Sometimes you can get off the shelf boards that'll do what you want, but that's not always possible, and those are generally pretty bespoke. A lot of times these systems are ARM processors, or we've seen some PowerPC processors, so that's going out of style. Sometimes you get x86 processors in there, but that's reasonably rare. And while they'll run Linux, sometimes you'll get other operating systems like QNX, VxWorks. Sometimes you'll run a much more bare metal RTOS or no operating system at all. It's actually something else that happens. So what does development look like for these machines? Generally, you start by programming something up on your laptop or desktop, trying to make sure that you've got code that'll work and that you're comfortable with. When you're happy enough there, you'll cross-compile on your laptop for the target and produce a binary, and then you can copy it over to your target and run it and see how it performs. So if we look at what Bazel is going to do when we build a target, this target, for example, I'm using the protobuf compiler to make it a little more interesting. So the first thing we have to do is we have to build the protobuf compiler. That'll generate the proto-C binary. From there, we can run that protobuf compiler to generate our .pb.cc and .pb.h files that we then want to build with our compiler again and build them for our target, which will be our laptop in this case, and then produce a final binary. If we look at how that changes when we're doing our cross compilation, a lot of it actually stays the same. We still need to build the protobuf compiler and generate our .pb.cc and .pb.h files. And then we'll use, in this case, ARM Linux EABI GCC. This is a cross compiler that'll take our source code and generate ARM binaries. And then we can use that to generate our ARM target. Bazel understands three platforms when you're building. There's your host platform. This is the place where the Bazel client is running. There's your execution platform. This is the place where Bazel runs the compilers. And then there's your target platform. And this is what Bazel is trying to produce executables for. If we look at a super simple case here, I'm going to be doing everything on my laptop. So I'm running my Bazel client on my laptop. Bazel's then going to run the compilers on my laptop. And then I'm trying to build binaries for my laptop. So all three of those targets are my laptop. If we're going to do a cross compilation on my laptop, it's going to be slightly different. So the host and execution platforms stay the same. We're going to still be running Bazel on my laptop and running the compilers on the laptop, but you're then trying to generate binaries for your embedded platform. If we look at a remote build, so we're going to hook Bazel up to a remote execution cluster. You're going to run your Bazel client on your laptop, but you're going to actually run the compilers on your servers. And then depending on how you set it up, you'll run your targets. You'll be trying to target your server as well. And if we do go full hog here and we try and do a cross compile with our remote execution system, we'll be running Bazel on our laptop, but the compilers run in the cluster and we're targeting our embedded system. So there's generally 3 ways that I've found so far through my exploration through the last 4 years for how to try and test with embedded systems. So one, we can try and run Bazel on our target, try and run it on our embedded system. Another strategy which we'll explore is we can build cross binaries with Bazel on a server, and then we can copy the binaries over to a platform and try and run them. Or we can figure out how to use remote execution. So Bazel running on the target is not always super straightforward. Bazel distributes a large number of binaries for a large number of targets, but they don't necessarily have to include your target. And this has gotten better over the years. If you get past that and you find a version of Bazel or you build your own, you're going to start to run into certain rules have checked-in binaries. So we quickly learned that rules node.js has an x86 node checked in there down on the bottom. Rules goes a little better. It has a bunch of different Go compilers checked in that you can use for different architectures. You may or may not have the one you need. Rules Docker has similar challenges. There's some executables it needs. If you go look at Rules Docker and dig deep down in the guts, you're going to find it's going to download a Go puller, which is for downloading Docker containers. And you can see here, this is a pre-built Go puller for Darwin. So this is the type of stuff you'll find where it was just too hard for somebody to build all this from source as part of the build. If you get through all that and you have a build, you're going to start to learn that your embedded system is not all that fast. Some of the ones that I've worked on have 128 mega RAM or even less. And if they have 1 or 2 cores and some pretty slow disk, that gets to be a pretty sluggish build, which makes you question if that's really the right answer. And then it's a little tricky then to start to get developers access to platforms so they can test. When I've done this, it's taken a couple hours generally to get everything reset up every time you have to go debug a embedded system problem. And just pretty quickly, you start to ask yourself, am I doing the right thing? And it feels like I'm fighting the flow. Is there a better way? So our second strategy we were talking about is there's a flag called run under, where you can tell Bazel, run your executables under this script, use the script to run them. And we could go code up a script that goes and copies the executables to our target and then runs them and copies the results back. And pretty quickly, you start to want to scale it up. So how do I have multiple of these targets I can run work on? Networks aren't perfect, so how can I start to deal with retries? And I want to cache the results. And this is starting to sound awfully like remote execution. And you'd really like Bazel to manage more of this because it already knows how to do a lot of this for remote execution. So this one just doesn't scale super well. So we get down to trying to hook up a remote execution cluster. So really what we want is we want to take our laptop, have it connect to the cluster, and have x86 servers for doing our big builds, and then embedded platforms in there where we can actually run the tests as the final step. And then we can distribute this all. And this does work. So a simplified view of how remote execution works. So the Bazel client first starts by uploading the inputs to your build. So here we're going to upload foo-test.c, make sure that's in the cache. It doesn't upload if it's already there. And then from there, the client says, okay, I have this action for you to run to do a compilation step. So take that foo-test.c that you know about, run this compiler. Here's some output I want you to put back in the cache and potentially give me back later, and then run it on this platform. So the cluster then goes and runs that action, generates foo-test, the binary, puts it back in the cache, tells the client that it succeeded. And then the Bazel client says, okay, next, let's go and run that test. So it goes and sends out an action for foo-test to run it. And then the worker goes and grabs that from the cache again, runs it, pushes the results. So if we add embedded workers, this gets slightly different. A lot of the first steps all stay the same. We do the same build. We upload the artifact. We go trigger the build of that artifact on the worker. That gets put in the cache. And then for our running of the test, we actually just specify that we want it to run on a different platform. So we say, hey, we want that one on ARM, not x86. And so then it will schedule it on the embedded worker, run it, and push the results in the cache, and then tell the client that this succeeded. There's another cool thing we can do with this if we want. We can actually go and hook up little microcontrollers to some of these workers. I've done this before to pretty good success. So you build your test into a little piece of embedded firmware that's going to go run your test and prints the results out. So your worker then knows to take that, uses a little script, flashes that firmware onto the microcontroller with your test, and then runs it, and then takes the result back over a serial port, for example, and then report success or failure back up into your cluster, and you're off. So this is how you can kind of get around the limitation of needing to run the entire worker stack on your worker. So how do we configure this? So we're running an ngFlow cluster. So for us, the documentation said add a second pool of workers. So we have our main pool of x86 workers, and then we added an ARM pool. And then in our platform configuration here, we added pool ARM into the exec properties. So now any actions that get annotated with this platform will get scheduled on our workers, our embedded system workers, and we're off. So benefits on this? Well, all this parallelism and caching, that all happens for free. Bazel and the remote execution system already know how to deal with this, so we're just along for the ride. It's super scalable too. You can just keep adding embedded systems, adding servers. You can add more types of systems if you want. All of that happens transparently on the back end and easy to scale up. The part that I really like is you're actually doing your compilations on fast x86 machines that can be in the cloud or wherever. And those can be cheaper and faster. And then the actual execution of the tests runs on the embedded platform that you care about. And a lot of your rules and stuff get a lot simpler. We don't need to modify as many things. And it's actually easy for developers to run tests too. They can just hook up to the cluster and go. So here's an example where I ran a test on my laptop against the cluster for our target system. So we did a Bazel test. We specified the target platform to tell us to do the cross builds, specify our test. And then because we're work from home and not everyone has good internet, we don't turn remote execution on by default. But here we want to say, hey, turn on all the remote execution flags to connect to the cluster. And it just magically works. Here you can see we ran this on the cluster and things were cached and things were actually successfully run. Downsides, you're now a bit off the maintenance of a remote execution cluster. That's not always free. You get other wins from doing that. You're also going to find a fair amount of sandbox leaks. We found all sorts of things that were installed on our laptops, but not necessarily sandboxed into the servers. I actually view this as a positive thing because it catches all the unknown dependencies and makes sure your build's more hermetic and reproducible. And because now you're a little bit more removed from running the test, it can be a little harder to get it under a debugger if something goes seriously wrong. There's a small asterisk to all this. Bazel test foo by default runs foo on the execution platform, not the target platform. This is a decision made from Bazel in the past. That's not necessarily what we want in this case. So what we did is we grabbed a patch from Ulf that goes and changes that, adds a flag to Bazel that makes it so that the platform that you're running the test on is the target platform, not the execution platform. And that's how we were able to steer those actions correctly. There's been some discussion in the Bazel community about what's the actual proper way to do this, and test execution groups appear to be the way forwards. So there will be some activity in this space, and hopefully we can get something figured out. So here's one of our builds from before. So it was a 45-minute build. This was reasonably average. There's 4 main builds here. We're building on x86 for x86 as a faster build. Then we're doing our cross build, but ignoring the results just to make sure there's no compiler errors. And then we run a subset of tests directly on our embedded system, which here you can see is the long poll. That was 44 minutes, whereas our other builds were about 21 minutes. And then we have a separate UI build because we couldn't figure out how to get that to work with all of this. When we switched over to running tests against our embedded system in our remote cluster, we were able to drop 2 of those builds. The UI build got consumed into the rest of the Bazel build, and we dropped running on our embedded system, and we're able to run the tests directly. And we got significantly faster. So our embedded system tests are now much more parallel and cached and all those great things, which is a huge win. So we saw our worst case builds before where you hit that core.h header file that rebuilds the worlds. We're hitting us at about 2 hours. Those worst case builds now come in at about 25 minutes, which is not significantly more than the average build, which is pretty awesome. We've been able to move all of our builds over to Bazel and dropped everything else. So there's just a lot less interactions to work with. And everything's gotten a lot easier to maintain. We have fewer patches to third-party rules. We're just much happier. And what more can you ask for? So thank you for coming. Hopefully you learned something about how to think about embedded systems testing with Bazel and got to see part of the journey I've been on in this space for the last 4 years.